Nobody told you the truth about what really happens when two galaxies collide. The photograph arrived without ceremony on a Tuesday morning in 2006. Hubble had been staring at a patch of sky in the constellation Corvus for hours. What came back was not a star, not a nebula, not anything with a clean name. Two galaxies caught mid-collision, their spiral arms torn open and twisted into arcing tails of light stretching across hundreds of thousands of light years. The Andromeda Galaxies, designated NGC 4038 and NGC 4039, tearing each apart in a gravitational embrace that began 600 million years ago. And somewhere inside those twisted arms, billions of new stars were igniting, all at once born from the violence of the impact itself. This was not destruction, this was transformation on a cosmic scale. But to understand what is truly happening inside a galaxy collision, you first need to understand the almost absurd emptiness of space. A galaxy is not a dense solid object like a ball or a rock. It is an almost incomprehensible void, punctuated occasionally by stars. The Milky Way spans roughly 100,000 light-years across its disk. Inside that disk, approximately 200 to 400 billion stars orbit a common center. That sounds crowded, the numbers are staggering, but the average distance between stars in our galaxy's neighborhood is roughly 4 to 5 light-years, about 40 trillion kilometers of empty nothing. If the Sun were the size of an orange sitting in the center of Paris, the nearest neighboring star would be another orange somewhere in Berlin. Everything between them is vacuum, radiation, and the occasional dust grain. This emptiness defines what actually happens when two galaxies collide. It defines why the collision of two structures, each containing hundreds of billions of stars, does not result in hundreds of billions of catastrophic stellar explosions. The stars pass through each other's space like two swarms of bees merging. Individual bees almost never collide, but the swarm as a whole is transformed. The story of our own impending collision began not with panic, but with precision. In 2012, a team led by Roland van der Merel at the Space Telescope Science Institute published a landmark paper in the Astrophysical Journal. They had used Hubble to track the precise motion of stars in the Andromeda Galaxy, designated M31, the largest spiral galaxy in our local group. This was not a simple measurement. Andromeda sits 2.537 million light-years away. Its motion across the sky is so slow that detecting it requires years of careful imaging, comparing star positions against background objects with extraordinary precision. Van der Merel's team measured something that had been theorized but never confirmed. Andromeda is not merely falling toward the Milky Way along the line of sight. It has a measurable transverse velocity, a sideways drift perpendicular to our view. The full three-dimensional trajectory could finally be calculated with confidence. The conclusion was unambiguous. Collision is certain. Not a near miss. Not a gravitational interaction that bends trajectories and separates. A direct merger. The two largest galaxies in our local group combining into one. The numbers deserve attention because they are simultaneously enormous and deceptive. Andromeda is currently approaching at approximately 110 kilometers per second. That velocity sounds violent. It is, in a cosmic sense, actually rather modest. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the galactic center at roughly 220 kilometers per second. Everything in the universe is already moving fast. At 110 kilometers per second, Andromeda crosses a distance equal to Earth's circumference every 370 seconds. It covers the Earth-Moon distance in about an hour. Yet the distance separating us is 2.537 million light-years, approximately 24 quadrillion kilometers of intergalactic void. At 110 kilometers per second, covering that distance straight through would take about 7 billion years. But gravity is accelerating the approach constantly. The two galaxies are falling toward each other, speeding up as they close the gap. NASA's simulations, built using data from van der Merel's 2012 measurements, calculate the first direct encounter approximately 4.5 billion years from now. This is a number worth sitting with for a moment. The Sun is currently 4.6 billion years old. Life on Earth emerged roughly 3.8 billion years ago. In the same span of time it took for single-celled organisms to evolve into every living thing that has ever existed on this planet, Andromeda will have closed 2.537 million light-years. What happens at that first encounter is not what most people expect. Popular imagination pictures a galaxy collision as a catastrophic explosion, a wall of stars smashing into another wall of stars, everything annihilated in fire. The reality is stranger, slower, and in many ways more disturbing. The first pass takes several hundred million years to complete. The two galaxy disks interpenetrate at a steep angle, their stellar populations sliding through each other's space with minimal direct stellar contact. Actual star-to-star collisions during the merger are statistically nearly impossible. Dr. John Dubinsky at the University of Toronto ran some of the most detailed simulations of the Milky Way Andromeda collision ever attempted, published in Scientific American in 2006. His models required supercomputers running for weeks to track millions of test particles, representing stars, dark matter halos, and gas clouds across billions of years. The simulations revealed that the first pass does not end the encounter. The two galaxies shoot through each other, their momentum carrying them apart briefly. Then gravity reasserts itself. The galaxies slow, stop, fall back toward each other. A second pass occurs, more chaotic than the first. Arms more thoroughly disrupted. Then a third, a fourth, each pass shorter and more destructive than the last. The process of final merging takes not 4.5 billion years, but closer to 10 billion years. From today before a stable combined structure settles into equilibrium. But during those passes, something extraordinary happens to the stars themselves. Not to individual stars in the sense of physical destruction, to their orbits, their trajectories, their relationship with the galaxy they call home. Gravity during a merger does not distribute its effects evenly. Stars in certain orbital configurations experience gravitational tugs from the approaching galaxy that amplify over time. Small perturbations growing with each successive pass. Some stars are flung inward toward the galactic centers. Others receive gravitational slingshots of extraordinary power, boosting their velocities far beyond the escape velocity of either galaxy. These stars are ejected entirely, launched into intergalactic space on trajectories. They will follow for billions of years, never returning to any galaxy. Dubinsky's simulations showed that a significant fraction of both galaxies' stars, potentially 5 to 10% of the total stellar population, end up as intergalactic exiles. Lone stars drifting through the void between galaxies, orphaned by gravitational violence, traveling through darkness that contains no neighboring star for millions of light years. The antennae galaxies we observe today show exactly this process happening in real time. Those long antenna-like tails of stars curving away from the collision point are ejected populations, stellar communities being flung away from their home galaxies permanently. Here's where the story becomes personal in a way most documentaries do not discuss. The solar system is one gravitational object among hundreds of billions in the Milky Way. During the Andromeda merger, every one of those objects faces a probabilistic future. Simulations by Cox and Loeb at Harvard, published in the Astrophysical Journal in 2008, attempted to calculate specifically what happens to solar system-sized objects. Their models were the most detailed attempted for this specific question at that time. They tracked test particles representing the Sun's current orbital position through the entire merger sequence, running the simulation multiple times with slight variations. The results were not comforting. There is approximately a 50% probability that the solar system ends up in a dramatically different location after the merger is complete. Not just a different neighborhood within a merged galaxy. In some simulation runs, solar system-like objects ended up ejected entirely, launched into intergalactic space, and severed from any parent galaxy permanently. In others, they were flung to the extreme outer halo of the merged structure. Tens of thousands of light years from any galactic center, isolated in near-total darkness. In the most optimistic outcomes, they remained somewhere in the combined galaxy's disk, perhaps in a region that had originally belonged to Andromeda rather than the Milky Way. The probability of remaining within a few thousand light-years of our current position. Essentially zero. Everything changes. The only question is how drastically. To understand why gravity can do this to individual stars, you need to understand something called the three-body problem and why it makes orbital prediction impossible. When two objects interact gravitationally, the mathematics is clean and solvable. Newton solved it in the 17th century. Orbits are stable ellipses. Prediction is perfect. Add a third object and everything changes. The equations have no general closed-form solution. Poincaré proved this in 1890, and the proof earned him a prize from King Oscar II of Sweden. When a galaxy contains hundreds of billions of objects all interacting gravitationally, prediction of any individual orbit over billions of years becomes fundamentally impossible. Small differences in initial conditions lead to wildly different outcomes over time. This is not a limitation of our computing power. It is a mathematical fact about reality. The solar system's fate during the Andromeda merger is genuinely probabilistic, not merely uncertain due to incomplete data. The future branches into multiple possibilities. Cox and Loeb's percentage figures represent frequencies across many simulation runs, genuine probabilities emerging from the chaotic sensitivity of gravitational dynamics. Now consider what each of those outcomes actually means for anything living on Earth. The most immediate impact is not the merger itself, it is what happens to the gas. While stars pass through each other's space without colliding, gas clouds do not. Gas is not a point particle. It is diffuse, extended, compressible, and subject to shock waves. When two gas clouds collide at hundreds of kilometers per second, the gas compresses violently. Compression raises temperature and pressure. Temperature and pressure trigger star formation. The first pass of the Milky Way and Andromeda will trigger a starburst event of staggering scale. Instead of the Milky Way's current rate of producing roughly 2 or 3 new stars per year, the merger will temporarily produce hundreds or possibly thousands of new stars annually. Massive stars born in this starburst burn hot, live fast, and die in supernovae within millions of years. The combined galaxy during the merger will temporarily blaze with ultraviolet radiation. From millions of massive young stars forming and exploding across its tangled structure. This is exactly what we see in the antennae galaxies right now, confirming the prediction. What does a starburst event mean for any planetary system caught inside it? New massive stars are dangerous neighbors in ways small, stable stars like the Sun are not. Their intense ultraviolet radiation strips atmosphere from nearby planets. Their supernova deaths produce shockwaves of radiation traveling at significant fractions of light speed. At sufficiently close range, a supernova can sterilize a planet, destroying the ozone layer, and exposing the surface to lethal doses of ultraviolet and gamma radiation. In a normal galaxy like the current Milky Way, supernovae are rare enough to be survivable, in a probabilistic sense. Earth has likely endured multiple nearby supernovae over its history. During a starburst merger, the rate increases dramatically. But here's what the models actually show about habitability. Even during peak starburst activity, the probability that the solar system itself ends up within lethal range of a supernova remains relatively low. Space is still vast. Most supernovae happen in different regions of the colliding structure. The greater threat to life is not radiation. It is gravitational disruption of orbits. The outer solar system is held together by gravity that is, in cosmic terms, rather fragile. The Oort cloud, the vast spherical shell of cometary bodies extending out to perhaps a light year from the Sun, is barely gravitationally bound to our star. During close approaches between the merging galaxies, tidal forces could disrupt the Oort cloud, dramatically sending showers of comets plunging into the inner solar system. This is not speculation. It has happened before on a smaller scale. When the Milky Way absorbs smaller satellite galaxies, tidal disruption events affect the outer edges of stellar systems throughout the region of closest approach. A full-scale merger with Andromeda would produce tidal effects orders of magnitude larger. The inner solar system, however, is far more tightly bound. Earth orbits 150 million kilometers from the Sun in a gravitational well so deep that no realistic tidal force from a passing galaxy could dislodge it directly. The threat to Earth specifically comes not from the merger itself, but from long-term orbital chaos. Dr. Konstantin Batygin at Caltech published research in 2015 on the long-term stability of the inner solar system, separate from but relevant to the merger question. His simulations showed that even without external perturbations, the inner solar system has a small but non-zero probability of destabilizing on timescales of billions of years. Mercury's orbit is the most vulnerable, its slight eccentricity able to grow through gravitational resonances with Jupiter until catastrophic outcomes become possible. In roughly 1% of Batygin's simulations, Mercury eventually collided with Venus or the Sun, and in a small fraction of those, the subsequent disruption threatened Earth's orbit directly. Add the gravitational perturbations of a full galactic merger, and those probabilities increase. Not to certainty, not even to likelihood, but to something more than negligible. The solar system as we know it will probably survive the Andromeda merger intact. Probably. That one word carries enormous weight when Earth is the subject. By the time the first pass occurs 4.5 billion years from now, the Sun will be dramatically different. Stars do not maintain constant brightness throughout their lifetimes. The Sun is currently in the middle of its main sequence phase, burning hydrogen in its core. Over the next billion years, the Sun's luminosity will increase by roughly 10%. Over 4.5 billion years, it will have increased by perhaps 40% compared to today. Earth's surface will almost certainly be uninhabitable long before Andromeda arrives. The habitable zone around the Sun will have shifted outward, perhaps to the orbit of Mars. Oceans may have evaporated completely, the runaway greenhouse effect that turned Venus into a hellscape may have already claimed Earth by the time galaxies begin to merge. This timeline matters enormously for any honest discussion of what the merger means for life. The civilization-ending threat from the Andromeda merger is essentially irrelevant, because Earth loses habitability billions of years before the merger reaches peak violence. The galaxy collision is not humanity's apocalypse. The Sun is. What the merger does threaten is not life on Earth, but life anywhere in the merged galaxy. Any planet that currently orbits in a stable temperate location could be disrupted. Over the 10 billion year merger process, its orbit changed by gravitational perturbations. Any star ejected into intergalactic space carries its planetary system with it into the void. Those planets are not destroyed, they continue orbiting their stars. But cut off from the galactic ecosystem, their stars will eventually exhaust their fuel, and their planets will freeze or burn depending on the star's fate. Life, if it existed on those planets, would need to survive on whatever resources its isolated solar system contains, with no possibility of ever reaching another star system. The galaxy merger is an extinction event not through direct violence, but through separation. It scatters the building blocks of future civilizations across impossible distances. The gas clouds disrupted during the merger tell another part of this story. Gas in both the Milky Way and Andromeda is not evenly distributed. It concentrates in spiral arms, in molecular clouds, in dense regions where conditions favor star formation more than in the spaces between. When the merger scatters and compresses this gas, some regions lose their gas entirely, blown outward by stellar winds and supernova pressure waves. Other regions accumulate more gas than they have ever contained. The merging system briefly becomes one of the most productive star-forming regions in the observable universe, a starburst galaxy comparable to the infrared luminous systems. JWST now observes at high redshift the early universe counterparts of what we will become. The new stars born during this starburst include stars of all masses. Most will be small red dwarf stars that will burn for trillions of years into the future. Around some of those new stars, new planets will form from the enriched gas and dust. The merger is simultaneously a mass extinction of existing planetary systems
The merger is simultaneously a mass extinction of existing planetary systems.
There is a specific observation that makes all of this more than theoretical. In 2019, astronomers using the Hubble Space Telescope published data from the Andromeda Galaxies showing star cluster formation rates in extraordinary detail. The paper, published in the Astrophysical Journal by Linden and colleagues, mapped thousands of star clusters forming throughout the collision zone. Ages of the clusters showed a clear pattern corresponding to the merger timeline. Oldest clusters formed before the galaxies encountered each other. A middle generation formed during the first interpenetration triggered by shocked gas. The youngest, most massive clusters were still forming in the densest collision zones. This was not a simulation. This was direct observation of galaxy merger consequences, frozen in time by the light travel time from 45 million light-years away. The antennae show us our future in observational data, not theoretical models alone. Our galaxy will look like that. Our sky will eventually contain those twisted tails of light. Simulations of the specific Milky Way Andromeda merger have grown increasingly sophisticated. The 2012 Cox and Loeb paper established the baseline timeline and probability distributions, but computational power available to cosmologists has increased dramatically since then. In 2019, a team at the Heidelberg Institute for Theoretical Studies ran what they called Illustrist-NG, a massive hydrodynamic simulation of galaxy formation and evolution. That included merger events with gas physics, magnetic fields, and stellar feedback. Their results refined the timing and character of the Milky Way Andromeda merger. The simulations showed that the merger will produce an elliptical galaxy, the merged remnant losing its spiral structure as stars redistribute into a pressure-supported spheroid rather than a rotationally supported disk. The product has been given a colloquial name by astronomers, Milkomeda. The concept is entirely grounded in data. The object will be real. An elliptical galaxy is fundamentally different in character from the spiral we inhabit. Spiral galaxies are disk-shaped because gas cools efficiently and settles into a rotating plane. That gas disk continuously forms new stars, maintaining the galaxy's bright, active character. Elliptical galaxies form when mergers disrupt the gas disk, converting ordered rotation into random stellar motions that cannot easily settle back into a coherent plane. Without a coherent gas disk, new star formation essentially stops. The merged galaxy will gradually exhaust whatever gas remains over the following billions of years. New stars will stop forming. Old stars will age, the most massive ones dying first, leaving the galaxy increasingly dominated by dim, long-lived red and white dwarf stars. The night sky in Milkomeda, if any civilization survives to observe it, will gradually grow darker over billions of years as stellar populations age without replacement. This is the long-term fate of almost every galaxy in the universe. Mergers end spiral structure, ending star formation, leading inevitably to a cold, dark remnant. The two central black holes deserve their own chapter in this story. The Milky Way's central black hole, Sagittarius A, has a mass of approximately 4.1 million suns. It was confirmed visually by the Event Horizon Telescope collaboration in 2022, the first direct image of the shadow of a black hole in our own galaxy. Andromeda's central black hole, M31 Dartali, is far more massive, somewhere between 100 million and 200 million solar masses, making it 25 to 50 times larger than our own. When the galaxies merge, these two black holes do not immediately collide. They sink toward the center of the merged galaxy through a process called dynamical friction. Dense stellar populations surrounding each black hole are scattered by gravitational interactions. These interactions transfer energy and momentum from the black holes to surrounding stars, causing the black holes to spiral inward toward the combined gravitational center. This process takes hundreds of millions of years after the galaxies have merged visually. Eventually, the two black holes form a binary system, orbiting each other at decreasing distances. The final parsec problem is a famous complication in this scenario. Dr. Miloš Milosavljević and David Merritt published the definitive analysis of the final parsec problem. In the Astrophysical Journal in 2001, a paper cited thousands of times since. As a black hole binary tightens, dynamical friction becomes less effective. The binary runs out of stars to scatter once it clears the stellar population. From its immediate neighborhood, a region measuring roughly 1 parsec across, without stars to scatter, the binary has no mechanism to lose the remaining energy needed to bring the two black holes into gravitational wave emission range. In theory, the merger stalls. In practice, something must resolve the problem. Real observations show that black holes do merge. The stall cannot be permanent. Possible solutions include non-circular stellar orbits that continuously repopulate the cleared region with new stars to be scattered outward by the binary. Gas inflows driven by the merger itself could provide a viscous medium that extracts energy. Triaxial galactic potentials after the merger might provide chaotic stellar orbits that funnel stars efficiently into the region needed to drive the binary inward. When the two black holes finally do close the gap completely, the universe will hear it. Gravitational wave emission from a supermassive black hole binary is unlike anything detected by current instruments. LIGO detects gravitational waves from stellar mass black holes merging. Objects ranging from a few to 100 solar masses, producing waves at frequencies of tens to hundreds of hertz, well within current detector range. A Sagittarius A and M31 Narch merger would involve objects of 4 million and 150 million solar masses. The gravitational waves from this merger would have frequencies in the nanohertz range, wavelengths spanning light years, completely invisible to LIGO's kilometer-scale arms. The Pulsar Timing Array, a network of pulsars used as a gravitational wave detector across galactic scales, detected evidence of a gravitational wave background in 2023. That background is thought to include contributions from exactly this type of merger, supermassive black hole binaries in merging galaxies throughout the observable universe. The Sagittarius A and M31 merger, happening roughly 10 billion years from now, will produce one of the most powerful gravitational wave events the universe generates. Whether anything will exist to detect it is a different question entirely. Let us return to the sky itself, because the visual transformation will be extraordinary. About 3.75 billion years from now, Andromeda will have grown visibly larger than the full moon in Earth's night sky, assuming Earth remains habitable at all. Currently, Andromeda spans roughly 3 degrees of arc, about 6 times the moon's width, but it is too dim to see with the naked eye under most conditions. As it approaches over billions of years, its angular size grows to fill significant portions of the sky, eventually becoming the dominant feature of any night view. At around 4 billion years from now, the first gravitational distortions will become visible. Andromeda's spiral arms will show the beginnings of tidal disruption, stretched and pulled by the Milky Way's gravitational influence pulling at material on the near side. Simultaneously, the Milky Way's own spiral structure will begin showing equivalent distortion. At 4.5 billion years, during the first pass, the sky will contain what can only be described as a second Milky Way, crossing the entire sky at a steep angle above and below. 2 bands of stars, 2 rivers of light, intersecting overhead in every direction. Stars flung by the encounter will create visible streams and shells across the sky. No human eye will see this, almost certainly, but some form of intelligence might. This sky transformation is not unprecedented. We observe it happening to other galaxies. The galaxy NGC 5128, also called Centaurus A, is one of the most studied radio galaxies in the sky. It lies approximately 12 million light-years away. Centaurus A is an elliptical galaxy with a dark lane of dust cutting across its center. That dust lane is the remnant of a spiral galaxy that was swallowed by the elliptical. The spiral galaxy does not exist anymore as a separate structure. It has been absorbed, but its gas and dust persist in that dark band, still being processed billions of years later. The Milky Way will eventually become an object like Centaurus A. Our galaxy's history encoded in faint stellar streams and residual dust structures. Future astronomers in some distant galaxy, if they exist, could read our history in the shell structures of Milky Way billions of years after the merger is complete. The dark matter halos of both galaxies play a role that is often underestimated. Visible matter, the stars and gas we can directly observe, represents only a fraction of the total mass of any galaxy. The Milky Way's dark matter halo extends perhaps 300,000 light-years in radius, far beyond the visible stellar disk. Its total mass is roughly 1 trillion solar masses. Andromeda's dark matter halo is even more extensive, potentially extending to 600,000 light-years and containing 2 trillion solar masses of invisible material. These halos began interacting long before the visible galaxies become visually disturbed. The initial gravitational influence between the Milky Way and Andromeda has been felt for billions of years already, slowing both galaxies relative to the cosmic expansion and ensuring their eventual merger despite the universe's overall expansion. During the merger, the dark matter halos interpenetrate and remix in ways that take far longer to settle than the visible stellar populations. Simulations show the dark matter halos achieving final equilibrium only billions of years after the stellar populations have merged into a coherent elliptical structure. The dark matter story of the merger is longer, quieter, and less visible than the stellar one. There is a philosophical question that haunts every discussion of deep time events. When we say the Andromeda collision will happen in 4.5 billion years, we are describing a future so remote that no direct human continuity can span it. The gap between now and first contact is greater than the age of the Earth, greater than the entire span of time from the formation of the solar system to the present day. Every human civilization that has ever existed fits inside the last 0.0001% of the time remaining before the first encounter. Ancient Rome, the pyramids of Egypt, the invention of writing, all of recorded history, a microscopic sliver compared to the weight. This raises the question of whether calling it our future is even meaningful. The sun that will exist at first contact is not quite the same sun as today, heavier elements gradually accumulating in its core, changing its interior structure. The Earth, if it still exists, will have been geologically reshaped entirely. Every continent will have moved, collided, and separated multiple times. Species alive today will have been extinct for billions of years. Whatever inherits the solar system by then will look back at us the way we look back at Cambrian trilobites, distant ancestors barely recognizable, separated by incomprehensible time. And yet the physics does not care about these philosophical complications. Andromeda is approaching at 110 kilometers per second right now, as you read these words. Every second, it closes the distance by 110 kilometers. It has been doing this for billions of years, long before the Earth formed. It will continue doing this regardless of what happens on any planet in either galaxy. The merger is not a future event waiting to begin, it is already in progress. The mutual gravitational influence has been shaping both galaxies for billions of years. The Milky Way and Andromeda are already participating in a slow-motion cosmic dance, whose choreography was determined billions of years ago by the initial conditions of the local group's formation after the Big Bang. The local group itself deserves a moment of attention. The Milky Way and Andromeda are the two dominant members of a collection of roughly 54 galaxies gravitationally bound together in a region, spanning about 10 million light-years. Members include the Triangulum Galaxy M33, a smaller spiral that may participate in the merger, with simulations suggesting it will eventually be absorbed into Milkomeda as well. The Large and Small Magellanic Clouds orbit the Milky Way and will also eventually merge. Over the same timescales as the Andromeda merger, the smaller galaxies of the local group will all be absorbed into the growing Milkomeda structure one by one. What was once 54 distinct galaxies will eventually become one massive elliptical galaxy, containing the combined stellar populations of all its predecessors. Beyond the local group, the universe's accelerating expansion is already carrying other galaxy groups beyond any future possibility of gravitational reunion. Milkomeda will eventually be alone, an island universe in a dark and expanding void. In November 2021, the Gaia mission released its early data Release 3, providing proper motions for over 1.5 billion stars in and around the Milky Way. Among the data were improved measurements of dwarf galaxies and stellar streams that constrain the Milky Way's total mass and the shape of its dark matter halo. A more precise Milky Way mass means more precise gravitational dynamics in merger simulations, improving the reliability of outcome predictions. Follow-up work using Gaia data by Solomon and colleagues in 2022 refined the mass of the Milky Way's dark matter halo to approximately 1.17 trillion solar masses, improving confidence in merger timeline calculations substantially. ESA's Gaia mission has transformed the precision of these calculations by providing measurements that simply were not possible from Earth's surface. Each incremental improvement to our knowledge of these galaxies' properties translates directly into improved merger predictions. The ancient Greeks imagined the Milky Way as divine milk spilled across the sky. The word galaxy comes from the Greek word for milk, gala, encoded in our language permanently. They had no concept that the faint band overhead was composed of hundreds of billions of stars. No concept that it had a shape, a center, a rotation, a history of its own. No concept that the faint smudge near Perseus was not a cloud, but an entire separate galaxy, as large as our own, containing its own hundreds of billions of stars and worlds. Andromeda has been visible in human skies for as long as humans have had eyes to see. It is the most distant object visible to the naked eye, a faint oval smudge, slightly larger than the full moon in dark skies away from city light. For all of human history, that faint smudge has been approaching, closing the distance by 110 kilometers every second through every human civilization, every war, every discovery, every generation's birth and death. It was approaching when the pyramids were built, when Rome fell, when Newton formulated gravity. It will continue approaching long after the last human civilization has been forgotten. What does knowing about the Andromeda collision actually change? Not the practical circumstances of anyone's life, not policy, not tomorrow's decisions, but knowing changes something more fundamental than practical circumstances. It inserts our moment in time into a larger narrative that extends both directions infinitely. We are living between two events: the formation of the solar system 4.6 billion years ago, and the first collision with Andromeda 4.5 billion years hence. Roughly the midpoint of Earth's potentially habitable window, the universe is neither very young nor very old from our planet's perspective. We exist in what might be the golden age of the solar system, the middle of the stable period. Before us, the violence of formation; after us, the violence of collision and solar aging. Right now, a window of extraordinary stability, long enough for intelligence to emerge, brief enough to be precious in the context of cosmic time. The simulation results carry one specific number that deserves the final word. In Cox and Loeb's 2008 analysis, after the full 10 billion year merger is complete, after Milkomeda has settled into its elliptical form, after the black holes have merged, one question remained about the fate of solar system-like objects. What fraction of simulation runs ended with objects still orbiting within the combined galaxy, rather than being ejected into intergalactic space forever? The answer was roughly 94%. 94% chance the solar system remains gravitationally bound to the merged galaxy. 6% chance of complete ejection into intergalactic darkness and isolation. Those are better odds than many things we worry about on short timescales. But the 94% who remain in the galaxy will occupy dramatically different positions, different distances from the galactic center, different stellar neighborhoods entirely, different night skies, with no familiar constellations, no recognizable structures remaining. Whatever exists there will inherit a galaxy it did not recognize as home. It will orbit in a structure that had no existence when the solar system first formed. This is the honest truth about what happens when two galaxies collide. Not an explosion, not a catastrophe in the conventional sense, not a sudden end. A transformation extending over 10 billion years, slow beyond human comprehension, violent beyond human experience, producing from two spiral galaxies, one elliptical structure that will outlast both its parents by incomprehensible spans. The stars in Andromeda tonight are the same stars that will one day share a galaxy with our Sun. The generations of stars in those systems, if any have planets, if any have life, are already fated to become our galactic neighbors in the deepest possible sense. The merger is not a threat approaching from outside, it is a reunion. Two spirals assembling from the same gas cloud, 13.8 billion years ago, separated by the initial expansion of the universe, now falling back together, under the gravity that always connected them across millions of light years. Milky Way will not remember being two galaxies. But the light from those first stars, the gravitational memory encoded in stellar orbits, the chemical elements forged in generations of supernovae throughout both galaxies' histories, all of that will persist mixed together in the body of the merged system. We are 4.5 billion years from the first contact, staring at a smudge in Perseus, watching the largest thing that will ever happen to our galaxy approach at 110 kilometers per second. And the remarkable fact is not that it is coming. The remarkable fact is that we figured it out, that beings who live for 80 years on a planet around one of 400 billion stars looked at a faint smudge in the sky and calculated its velocity, its trajectory, its future, and the probable fate of our own solar system within it. The universe has given us a front-row view of our galaxy's destiny, billions of years in advance. What we do with that knowledge will define what we were. Thank you for staying with us until the very end of this journey through deep time. If this exploration moved you, subscribe and stay for the next chapter of discovery. Your curiosity is what allows the universe to understand its own future.